Hey everybody, it's Mr. Carr again. Today we're going to be talking about 12.3 day one. In this scenario, we're going to be talking a little bit of not so much about our limits as well, but focusing more on what's leading us up to, which is finding what's called an instantaneous rate of change by calculating the slopes of tangent lines. So what do we mean by that? Well, an instantaneous rate of change is when we have something like this. If we have a graph of f of x at the point x f of x is a slope, it has a slope line m of the tangent line, okay, at the point x f of x given by this formula, okay, provided the limit exists. So what does this formula mean? Well, remember we talk about slope here. Slope is y2 minus y1 over x2 minus x1. So if I'm given like any point that's on the graph, like x f of x, if we find a second point, we're going to call it x plus h and f of x plus h. Okay. So instead of writing it as y2, I'm going to write it as f of x plus h. And instead of y1, we're going to call it f of x here. And that's going to be over x2, which is again that x plus h, and then minus x. So when you look at this, well, if I get rid of the parentheses, I can also cancel out these x minus x here. So the idea is that slope is going to be represented by f of x plus h minus f of x over h. And that's what this is right here. Okay. So as h approaches zero, now obviously when you look at this, h cannot actually equal zero. So you're going to see some weird things that happen in this next part. But the idea is that as we get closer and closer to zero, okay, then we can understand what is the instantaneous rate of change. And again, when we talk about rate of change, we mean something like this. What is the slope of the line right here? If I compare that to the slope of the line here or here, these are all like the tangent lines idea, okay? So slope of graph at a point, find the slope of the line tangent to the graph of y equals x squared plus 1 at the point 2, 5. All right. So again, we need to do this definition here. So I'm gonna write it down like this, where I like to keep it organized, where f of x is x squared plus 1, but then also write out what is f of x plus h. That is x plus h squared plus 1. So if I distribute out x plus h times x plus h, that is going to be x squared plus 2xh plus h squared, and then still plus 1 over here. Okay? So now, when I want to evaluate my limit here, my slope is going to equal to the limit as h approaches 0 of, that'll be x squared plus 2xh plus h squared plus 1 minus, this will be x squared plus 1. Okay, and that's all over h. So as we move on, the limit as h approaches 0, notice that if I distribute the negative sign, it's going to turn to x squared plus 2xh plus h squared minus 1, or sorry, plus 1 minus x squared minus 1, all over h. From here, look at what we can cancel out. We have a positive x squared and a negative x squared, positive 1 and a negative 1. So after doing that, I have the limit as h approaches 0 of 2xh plus h squared all over h. Okay? We have a common factor with h. Remember before, I said you can't actually plug in 0 algebraically, but what if we reduce this? What if we take it down to this level and then we get rid of h? Because if I have h here, h squared, so I'll turn into h, and then h is here, this will turn into 2x plus h. Okay? And when I evaluate it, when h is approaching 0, that means that h is going to go away, so it's just 2x now. So this is going to help me find my slope, because remember, we're defining my slope as the limit as we approach 0 between these two points here. So by taking my 2x, I can now find the slope, which is m equals 2 times x. And since we're going through the 0.25 here, that means the slope is going to be equal to just 2 times 2, which is equal to 4. Once we have the slope, we want to find then the equation of the tangent line, okay, that goes through the point. So I'm going to need a little bit more space here, so bump that up here a little bit. Okay. My equation is going to look like y equals mx plus b. So it's going to be 4x plus b. And since I have an xy 2, 5, we'll say 5 is equal to 4 times 2 plus b. 5 is equal to 8 plus b. Subtract that over, I get -3 for b. So my final answer here is, run out of space again, y equals 4x minus 3. There's my final one, okay? And that's really what we're doing today. We're defining our instantaneous slope as this limit, and we're going to work through and simplify these as best we can, all right? So same thing as before. If we want to find, I'm going to say f of x is equal to x squared plus 2x, which means f of x plus h is going to be x plus h squared plus 2 times x plus h. If I simplify this a little bit here, that's going to be x squared plus 2xh plus h squared plus 2x plus 2h. Okay, so now the slope, which is the limit as h approaches 0, of f of x plus h, which is going to be x squared plus 2xh plus h squared plus 2x plus 2h minus x squared plus 2x, all over h. Okay, so keep going, bring the negative signs through. So the limit as h approaches 0 will be x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x, all over h. So start looking for where can we simplify. We can get rid of x squareds. We can get rid of a positive and negative 2x here, and that's it. So that's going to simplify down a little bit. So the limit as h approaches 0 of 2xh plus h squared plus 2h all over h. Well, again, we have a common term of h and everything. So I can get rid of that. This will turn to h to the first power, and this will be gone away. So it's going to be a 2x plus h plus 2. And since h is approaching 0, that's just going to be 2x plus 2. Now, it says here, find the equation for the slope of the line. That's all we care about is finding the slope. So the slope is going to be 2x plus 2. What this is saying, don't forget, is that because it depends on what the x value. I have a quadratic. So roughly speaking, it looks like this. So the idea is that the slope of my tangent line changes based on my x value. Okay, that tangent line can go all over the place there. So having x equal to 4 versus x equals to -2 gives me different slopes there because it's a quadratic. Average velocity. So average velocity is telling us, basically we're looking at how much does it change over a given amount of time. Okay, so for example, we talk about, as an example, like we can say that if it takes you 1 hour to get from to drive 50 miles, does that mean you went 50 miles per hour the whole time? No, it means you average 50 miles because you were going a little faster, a little slower. Okay, chances are you went up and down a bit. So that's the idea here. So we look at average velocity as being the change in distance over the change in time, which is f of b, or I can call it y2 minus y1 over x2 minus x1. It's really just slope, but we're just looking at it in the sense of a moving object is what we're going to say. So that's what we're going to look at here. Average velocity of an object. So as part of a physics experiment, a ball is catapulted upward. The height of the ball is h of t equals -16t squared plus 95t plus 15, where t is in seconds and the height of the ball is measured in feet. What was the ball's average velocity between t equals 1 and t equals 2? So the idea here is that average velocity, so v average, is equal to h of 2 minus h of 1 over 2 minus 1. Okay, so what I'm going to do is I'm going to just go off the side. I'm going to figure out what is h of 2 equal to and what is h of 1 equal to. So h of 2 is -16 times 2 squared plus 95 times 2 plus 15. Okay, so I plug that in the calculator. I got h of 2 is equal to 141. H of 1 is going to be -16 times 1 squared plus 95 times 1 plus 15. So h of 1 comes out as a 94. So that means that when I find my average velocity, that's going to be my two y values, so 141 minus 94 over 2 minus 1, which is 1. So when I subtract those out, we get 47 feet per second. Okay, and that's actually it for today. Our focus again was Just got this layer here. Okay, our focus today was talking about instantaneous rate of change, and then we're finishing up with his average velocity. Okay, so again, all tied back to limits and rates of change like that. So that is it for today. Okay, take care, everyone.